Hi CJ, I'm here. Yes.
Good evening.
Good evening. How are you?
Mm, Tired. How are you?
Uh, could be better, but yeah, still okay. All right. Well, okay. Let me just share the Jamboard link with you for today. Yeah. Uh, okay. So what do you want
Thank
to
you.
do first? What do you want to do first? The question on the force, how to find it, or just go straight to
Oh,
topic five?
I already got the question I sent.
Okay.
So topic 5.
Topic five. All right then. Um. Okay. So let me just switch over to this. Mhm. All right, let's see if that works. Ah, that's weird. Okay, hold on. Okay, so hopefully that. Okay, can you see it? Can you see this clearly?
Hmm,
Let
I
me
can
just let me
see it.
just do that real quick. Okay, all right. So topic five. That's going to be electricity and magnetism.
Wait, I see myself.
Ah, oh, that's weird. Okay, better change that. Jamboard. Okay. Ah, hold on. Let me fix that. Ah, because it's on full screen. Okay. There. Okay. Should be good now. Should see the board. Like that. Alright. Uh
Hmm,
alright, so let's go. Let's just do this now. Alright. So electricity and magnetism. The idea, now the main idea here, mm, alright, is that well, electricity, you know what electricity essentially is? It's all about electrical charges, right? Now, the reason they're lumped together is because magnetism is actually also due to electrical charges. Okay, where is that thing? Okay, so um, okay, now in here, if we look at the contents of the syllabus here, it's taking a while to do that. Okay, um, electricity is basically two things. It's about either static electricity or electric currents, right?
hmm.
Or electric circuits. Now, magnetism in this particular top set of topics, okay, um, would be uh, all about electromagnetism. Okay, so root cause of magnetism and then electromagnetism. Okay, so you're pretty much I think you're pretty much familiar with all these topics, at least on a basic level, right? Okay.
Hmm,
Uh, I'm gonna guess at the very least you're familiar with magnetism a little bit, about electric circuits a bit, and electromagnetism just a little bit, right?
I think we only learned right now
Uh
static
huh.
electricity.
Okay, so what we'll do now, hold on. Okay, for static electricity, you probably started that. So what do you know about that now?
Static electricity is when you like Is it when you put a charged object and then transfer it,
Uh-huh.
or like transfer the charge onto the other object, and the like it just opens
Okay.
like the gold flakes, or like a leaf would go,
Ah, right. So
or is that electromagnet?
that's related to it, yes. That is part of what you learn in static electricity. Now, the key idea here for static electricity is that electrical charges, there are two main types, positive and negative, right?
Mhm.
Uh, just a bit of a history here, okay? So we know there are positive and negative charges, right? There are positive and negative charges. Okay. Now, you may be wondering a little bit, how do we know which one is positive and which one's negative, right?
Mhm.
There's a bit of history here. Okay, so let's kind of touch a bit on TOK here. How do we know which charges are positive and which charges are negative? Which charges are positive or negative? Ah, the history, it's actually gonna start this. We're gonna start the history with Ben Franklin. I guess you're familiar with who he is, right?
Mhm.
Benjamin Franklin. Now, the reason why his name comes up here is most of the time people associate his name with the lightning experiment, right? Okay. Now, however, for the context of static electricity, he contributed to this idea. He um, experimented with
Wait,
rubbing things together.
Benjamin Franklin or like Thomas Edison?
No, this is Benjamin Franklin.
Like the
The Benjamin
president,
Franklin.
like the
Yeah,
founding father?
yeah, the Benjamin Franklin.
Oh, wait.
Okay. Now, what he did is he experimented with rubbing things together. Okay. Now, he's one of the founding fathers for the United States. If I recall
Mhm.
right, the main reason why he was one of them is because he was a polymath. He was a person of many interests. And during those days, um, if you were one of those intelligent people, you really have to be a polymath at that time. Nowadays, if you're a really intelligent person, most of the time you go into academia, you focus on one particular topic, right? But back
Mhm.
then, you had to be interested in all the different things, including politics. That's why he's one of the founding fathers of the United States. But anyway, for me personally, because I'm not really from the States, right? I remember him mostly for being a sort of backyard scientist. But he was a really good backyard scientist. Okay. Now, going back here, what he did was he experimented with rubbing things together. Um, in particular, okay, he decided one day to rub amber on wool. Okay, that's the idea here. When he did that, so if we draw this a little bit here, so if this were the amber, and let's say that the wool is this, that's the wool. Okay, so what he did was he rubbed this amber back and forth onto the wool, and then when he separated them, upon separation after rubbing, right?
Mhm.
Upon he noticed he not well he noticed this a long time ago, but he um determined that um both objects were charged, right? And well, he came upon this particular problem. What do we call the charges? What will he call the charges? So he decided,
Q.
uh
Coulomb.
yeah, no, actually, Coulomb, the charge now is named after Coulomb. That the idea there was Franklin was not aware of the idea of charge yet, or electrical charge. Franklin was not yet aware of the idea of electrical charge. Well, not just Franklin, nobody was aware of the idea of electrical charge. Okay?
Mhm.
So, what he did was he called the thing charge. Okay. And then one more thing is he also gave Amber the positive charge. Okay. And Wool the negative charge. Okay. All right. And the naming stuck. The naming just stuck. Okay. So, however, there's something wrong with what he did. He thought that a positive charge had to be transferred.
It could be both, right?
Actually, no. It's the negative charge that's transferred. So,
Okay.
so what happened was, the Wool lost positive charges, right? Okay, charges, and the Amber gained the positive charge. Okay. Later on, we discovered that it's actually the electrons that are moving around and not, okay, and not this positive charge. So essentially, he was wrong on this aspect. Okay, but everything else that he came up with was eventually verified. Okay. There. Okay. So again, everything else that he came up with was verified. The only thing that wasn't true, according to him, was what was the thing that was lost and found. Okay. So anyway, so that's a TOK bit. That's how we know charges are charges. That's how we know charges are positive or negative. Okay. Now the rest of this, Franklin discovered and was rediscovered by other European scientists independently. So they didn't know of Franklin's works. That's why we call a lot of the modern things related to electricity after all those other scientists. Okay. So anyway, let's go back.
Wait, they found it around the same time period?
A bit later, but independently. They did not. They were not aware of Franklin's work at that time.
That's cool.
Okay. So anyway, or if they were aware of the idea, but not the small details yet. All right. So when they discovered the small details, like the charge of the electron, it was in fact the electron that was moving. They were named after those other scientists. Okay. But anyway, going back to the real part. So what happens with static electricity, right? Hold on, let me just check something to be sure. Okay, this one's pretty easy. What happens when you put two negative charges together?
Oh, they repel.
Okay, and so charges. Okay, so we know this from before. Like charges repel, right? And unlike charges attract.
Yeah.
Okay, this particular thing was discovered by Ben Franklin. Okay, however, he did not quantify it into a rule. He just said it like this. Okay. Now, who quantified it into a rule? This is where Coulomb comes in. Okay, Coulomb quantified the idea. Coulomb, okay, turned this relationship, okay, turned this relationship into an equation. Okay, specifically, the equation that he came up with is this: the force between between any two charges, so electrostatic force, is equal to, well, actually not equal to, it's proportional to Q1 Q2 over R squared. Okay, now what are these Q's? These are the magnitude, these are the charges. Okay, and the r would be the separation distance between the charges. Now, does that look familiar to you? Kind of familiar.
The equation, I mean, I don't think we draw Q or K like that.
Okay, now actually this is proportional to, right?
Yeah,
So
but like for us, they just added a K.
yeah, so of
It's
course,
n equals.
yes, correct. So basically, this gets turned into f e is equal to k q1 q2 over r squared,
Oh,
where this.
and
Go ahead.
the teacher compared this to the F equals GMM over R squared.
Exactly, I was gonna do the exact same thing. That's why I asked you if it kind of looks familiar, right? Because if you look at
Oh,
the gravitational equation, it's also the same idea. It's proportional to the two masses, mass 1, mass 2, the product of those two masses, and divided by their separation distance, right?
mhm,
So again, if
yeah.
you turn that into an equation, it becomes F equals G M1 M2 over R squared. So very similar,
Wait,
right?
yeah.
Okay.
I also wanted to connect this to like the do you know the TOK prompt?
What was the
The number 4. It's like, do we underestimate the challenges of taking knowledge out of its original context and transferring it into a different context? I
yeah?
wanted to use that example.
This is actually the thing. Yeah, as you mentioned. This is the other TOK thing. I wanted to go to this one before because it goes into the main idea of what TOK actually is. How do we know what we know, right?
Yeah,
All right. But the one you mentioned about TOK here is basically I'm gonna
transferring knowledge from its
yeah,
original context.
yeah. So transferring knowledge from an original context, from one context to another. I'll say it that way, right?
Yeah.
Okay. Now this is an example, a really good example of this thing, transferring that knowledge from one context to another. The story here is that Column realized, Column realized that he could try to do something with charges like what was did with masses and gravity. Try with
Mhm.
electricity what Newton did with mass. Okay, when he tried it out, he kind of came up with this rule, and then guess what? This worked. It worked. Okay,
Oh, it's his law.
yeah, that's why this law is now called Coulomb's law.
Yeah, is this law just a number or is there like a meaning behind it?
What does yeah, okay, what does this mean? So going back here, what does this mean in terms of, okay, if we state this in statement form, what does this mean? The force between two masses, right?
Mhm.
Two masses depends on the masses, right? And the square of the distance between them. Okay. Let's put product of the masses, right? Okay. So what the genius idea here from Coulomb is that this is basically the same idea. Instead of saying masses though, this is now charges, right? So he just changed the word masses to charges and it worked. Okay. Now, of course, one thing about this, we can further compare gravity and electromagnetism, right? So comparing gravity and electromagnetism, sorry, electrostatic forces, electrostatic forces. Okay, what he this still makes sense because if you think about this, I'm just gonna write the two things. Okay, F equals m g m 1 2 over r squared, and then the other one, let's put gravity here, right? Electrical force here would be equal to again K Q1 Q2 over R squared. Now, let's kind of add this idea as well. Masses are always... Oh, hold on. Did I disconnect?
No.
All right. It's just my Jamboard then. Okay.
Hello?
Yeah, I think I did disconnect.
Oh.
All right. I think it's come back. Okay. Let's see if we have that. Okay, that thing disappeared. I'm just gonna redo it. Okay, so let's just compare gravity. Fe equals big G small m m1 m2 over r squared to f. Sorry, that should be fg, right? And fe is equal to k q1 q2 over r squared. Now, the other thing I want to compare here is that remember that masses are always positive, right? We
Positively charged.
No, just positive. There's no such thing as a negative mass.
Oh, okay.
No such thing, at least that we are aware of, right? Okay. Now, that's something that's different between these two because charges can be positive or negative. Can be either positive or negative, right? Or, all right. So let's take a look at this. Now, I'm going to give you a slight correction for the gravity term, okay? Or the gravity equation. There should actually be a negative here, okay? Now, most of the time, even for IB, okay, most of the time, this negative sign is ignored. But you will see why we need a negative sign in a while, okay? Now, if you kind of, let's kind of, okay, I think I disconnected again. Hold on. Okay, there we go. Most of the time, this negative sign is ignored. Okay, now let's start off with the idea here in charges. If both charges are positive, then what the force Fe is negative, is positive, right?
Mm-hmm.
Okay, and we also know that they will repel each other. Repulsion, right? Now, can we say the same thing for the case wherein both charges are negative? Is it gonna be the exact same thing or different?
Um.
So if you have a negative charge and a negative charge, you put negative here and negative here, that kind of ends up being positive, right?
Yeah.
So it's still gonna be this, and therefore it will still be repulsion, which again makes sense from what we know, right? And here's the last thing about this. Okay, I'll put this here because I don't think we have enough space. Okay, if we have a positive and a negative charge, if charges are opposite, okay, so we have one positive and one negative. What does that do to the force? Does it keep it negative or positive?
Positive.
Okay, so remember, let's put that back here. So if this charge was positive and then this charge is negative, what would we get? What kind of number would we get?
Do you add it up or no?
You multiply them.
Oh, Oh, the negative.
Okay, so this is gonna be negative, right? Okay, negative. So what happens as well? Attraction, right? When opposite
Mm-hmm.
charges are together, they move towards each other, they attract each other, right? So let's kind of apply that idea here, okay, for gravity. So the only possible case is both masses are positive, right?
Mm-hmm.
Okay, both masses are positive. Now we know, hey, what happened to repulsion? Just put that here. Okay, so we know that two masses put together will attract each other, right?
Yeah.
Okay. Both charges are positive. Okay. Okay. So if both masses are gonna attract each other, so it's gonna be attraction. Okay. What also happens to the equation? What if we actually use that negative in here? If both masses are positive, the force is negative, right? So you see this sort of consistency. When the force is negative, it becomes attractive. When the force is positive, it becomes repulsive. Okay.
Yeah.
All right. So the negative sign here, which Newton actually had at the very beginning, we just tend to really ignore it. Okay. So it's still consistent that force is negative gives you attraction, force is positive gives you repulsion. Okay. Now, all right. So that's basically the TOK bits about it. So is that clear now why we compare electrical forces to gravitational forces?
It's similar, right?
Yeah, it
Because like there's still two quantities.
uh-huh. So similar in this case, similar because you have the r squared term.
Oh,
Sim
it's similar because you're still talking about like attraction and like
mm-hmm.
gravity being pulled towards each other.
Uh-huh. And
Like the pulling the planets towards each other.
yeah, this, right? The force being negative for both cases is always going to lead to attraction.
Mm-hmm.
Okay? And that means the forces being positive will lead to repulsion. This doesn't happen for masses because there's no such thing as a negative mass. Okay?
Mm-hmm.
But what if there were? If there were such a thing as a negative mass, then you put them together, they should repel. Okay?
Yeah.
All right. So anyway, so that's the TOK bit. Let's now go straight into the problems. Oh, by the way, the value of K before we do problems, okay? The value of K is 8.99 times 10 to the 9.
Was that just a random number he found? Like, how do you find that?
Okay. This number does it's not really random. It's actually let me put the unit in for real quick, okay? Newton meter squared per column squared. Okay. Now, this is not random because this is actually equal to 1 over 4 pi times a constant epsilon 0. Okay. This constant is called the permittivity of free space. Of free space. Okay. Think of free space as a vacuum. Okay. Okay. Now, what does
Yeah.
this mean? This this particular constant means. Okay. Oh, by the way, I'll just say this now. This has nothing to do with what you need to learn for IB. I just want to put it out here
Mm-hmm.
for just to be complete. Okay. Now,
Yeah.
this idea of the permittivity free space, this is a constant um, that determines basically how good of an insulator a vacuum is. Okay. All right. Um. Okay. Basically, beyond a limit. So this value will determine how many volts per unit distance, the voltage per unit distance, the minimum or the maximum voltage per unit distance is needed between charged objects, not particles in this case, but charged objects. Okay, before a spark is released. Okay. All right. So again, has nothing to do with IB. I just want to put it here just to give you an idea what it actually is. So this K is not some random value. It's actually got a physical significance here. Okay. Um. All right. One more thing about this. You can kind of easily remember this. Is a this rounds off to 9.00, right? 9.0 times 10 to the 9. 9 and 9. Okay. So if you want to do
Mhm.
a quick calculation, just do it like this if you can recall it. Okay. All right. So with that in mind, with that out of the way, let's go for some problems. Okay. Um,
Okay.
we will get to that problem. Okay, let's take a look at this work example from the textbook. So at this point in time, once you get past the TOK bits, all you really have to do is apply the formula, apply Coulomb's law. Okay. So for now, um, solve for the force between each charge.
Oh, do we just plug it in?
Yeah, just plug it into Coulomb's law.
So 8.99 times 8, and is it just times 8, not times 8 to the negative 9 or anything? Just times 8?
That's times 10 raised to 9. 8.99. Okay, again, let's write that here. K is 8.99 times 10 to the 9.
Yeah, but what about the 8, like the other 8?
Oh, this one?
Yeah,
Okay, you just put it in there. Okay, so basically what you
just
have to,
8?
yeah, this is your Q1 and Q2. However, you're in micro columns, not columns. So,
Then that means, wait, I got this.
mhm.
Got this. Times 10 to the 6, negative 6.
-6, correct. Anyway, it's in the data booklet if you need it. Yeah, if you for,
Mm-hmm.
but it is correct. That's 10 to the -6.
And for centimeters, do I
Have to,
just do 3 times 10 to the negative third, or do I just do
you,
0.3?
you can do
0.03.
0.03. It's either way is fine. Whatever's more comfortable for you, at least. Okay.
To change it to meters,
Yes, you still have to
do
change
I
it to meters.
do I always have to do 10 to the negative 3, no matter what number I'm on?
Not quite, because remember, centimeters is 10 to the -2. Centi is 10 to the -2.
Okay.
All right.
But why in this case I can do 10 to the negative 3?
You don't.
Oh,
You have to use 10 to the -2.
okay.
Okay. So, let me just calculate this. CJ, just so I just want to tell you right now, my laptop's starting to lag. I'm expecting it to crash soon. Okay? So if I disappear,
uh,
you know what happened, yeah?
yeah, okay. Are you planning to buy a desktop, like a just a PC?
Soon.
Yeah.
Yeah, because it's starting. Well, it's not that this laptop is bad, but it is quite old. It's in terms of laptop ages, 7 years is already old.
That no, that's pretty old. Yeah.
Yeah, but Still pretty powerful, so I think it can still run for another 3 years or so.
I think it could that could be like your work computer, and like your home computer should could be like the fun one. Not everything on one computer.
Yeah. All right, I think it's working now. Yep, everything's working
Yeah.
now. All
Yeah,
right.
because I bought my like desktop for
Mm-hmm.
like 4 or 5 years,
Right.
and like it's like budget, but it's still fine. Like
Yeah.
it's still running fast.
Actually, for desktops for the same power are a lot cheaper than laptops.
Yeah, yeah.
Uh, that's why I want to actually get a desktop. But with the way everything's set up for how I work and how I'm here in Indonesia, I'm not really in the Philippines or anything. Yeah, a desktop is not really an option right now.
You could get a small computer. Like
Yeah.
you could just remove the graphics card. Like you don't need that.
Mm-hmm. So
Yeah.
anyway, you have an answer yet?
I got 4.7 or 4.8 times 10 to the negative 9 for A.
Okay. Times
Um,
2, 6, negative. Hold on, let me just do the calculation myself. It's 8 exponent 6 negative. Okay, then divide that by 0.03 squared. Okay, what's your final answer?
for the A, it's
For A.
4.8 times 10 to the negative 9.
Uh-huh.
And for B, it's 9.6 times 10 to the negative 9.
Okay, let me put that here.
Is it
9.6,
wrong?
10 to the minus 9. Okay. Let me redo my calculation real quick, okay? So
Or like it's
do
more like 9.59.
9.59. Okay.
Yeah.
All right. I'm gonna redo this. Q1 is increased to 4. Okay. So 4 exponent negative 6 times Q1, right? So 8 exponent negative 6 times 8.99 exponent 9 divided by 0.03 squared. We have completely different answers. I have here 320 newtons. Okay. Now, let's compare notes. Let's compare notes on how we got it. Okay. So in my case, I did this. The electric force or the electrostatic force is equal to, let's just put the full formula in first. KQ1 Q2 over R squared. Right. Now, what's the K? That's
Uh, I
8.99.
forgot to square the R.
Oh, okay. Yeah, I think that's it then. Times 10 to the 9. That's K. Then our Q's here would be 4 times 10 to the 6 minus times 8 times 10 to the minus 6 all over 0.03 squared. So you said anything else that you got wrong except for squaring the.
Um, and also I forgot to put the times 9. Like
Oh,
um
this.
8.99 times 10 to the power 9. I
Okay,
don't know
so
how I forgot that.
okay. All right, so redo that, see if we get the same answer now.
Yeah, I got wait, for A I got
This is A and B.
one 160,
160. Yeah, that's correct now.
and it just got doubled.
Uh-huh.
Yes.
Okay.
I
So
wrote it down correctly, but I put it in my calculator wrong.
I see. Okay.
Yeah.
All right, just be careful with that then. Okay, so we'll just go straight here now. Fe equals same 8.99 times 10 to the minus 9, 10 to the 9. This time 2 times 10 to the 6. Yeah, times 8 times 10 to the 6, right? Minus.
Mhm.
Okay, all over 0.03 squared. That's gonna give you 160 newtons, right? Okay. Now, I'll show you a shortcut, just a real quick shortcut. Once you solved either one, you don't need to solve the other. Okay. Shortcut. Once one is solved, the other can be determined quickly. Right? Okay.
Mm-hmm.
Now, what's the shortcut here? Okay. Let's say that I'm gonna start with let's just put here equals 320 newtons, right? Okay. Now, let's say I'm gonna start with A, and I determined that the answer in A is 160 newtons, right? Now, here's the thing. This and this got doubled times 2. So from the equation, this means that the force is going to be 160 times 2. That's it. So that's going to give us a 320. Okay? So that's just a shortcut. If you can remember to use that, it's going to be useful. But if you don't, it's fine. You can always just use Coulomb's law again. Right? Okay. Um. All right. Where is my book now? Here. Let's do another one. Let's just do this one. Okay, this is again from the book. Let's see what. Let's see if you can solve this one. So you have a positive charge Q is placed on the line joining two other charges Q1 and Q2. So basically, it's still the same charges Q1 and Q2 in the previous example. So it's these two. Okay. Determine the distance from Q1 where this third positive charge experiences zero net force. Interesting. Um, okay. How would you draw this? So,
Okay, I
yeah.
draw, the
Okay.
line.
And then we put Q1 and Q2 somewhere, right?
I put charge Q on like the end. Oh,
Okay. So
okay,
one
sure.
here and one here, right?
Yeah.
So let's label that as Q1. And we know this is 2 microcolumns, right? This is
Mm-hmm.
Q2. And this is 8 microcolumns. So we're going to put Q somewhere here. Now, I want to ask you, where do you think Q would be, more or less? Where should it be? Should it be closer to
It should
Q1 or closer to
it
Q2?
should definitely be closer to Q1
Okay, so somewhere here. Why is that the case?
because Q2 is like 4 times greater, like charge.
Okay, exactly. All right. So we know that at this point it experiences two forces like that, right? So
Mm-hmm.
F from 8 and then the F from 2, right? Okay. How do you determine that now? How do you determine the distance from Q1? So you're looking at this distance D. Okay. Any idea how to do it?
Do we use that same equation? Oh, we do, we do.
Yeah, we do. But also we use one more thing.
You put 0 on F, no?
Somewhat
The
like
E
that.
is
I get the idea.
0,
Yeah. Oh, okay. I'm
no?
gonna say it in a different way. You're right. The force should be equal, right? F should be 0.
Yeah.
But the force, which force are we talking about? I can think of 3 forces. We have to be more specific.
FE.
The
What is E?
okay, the electrostatic force, right?
Mm-hmm.
But I see here 2 electrostatic forces. The force uh from the first charge and the force from the second charge. Let's just label that F1 and F2. Okay.
Yeah.
The missing term here is the sum of the forces or the resultant
Mm-hmm.
force. Resultant electrostatic force should be 0. It's the resultant important here. Okay, so we say here that the sum of the forces should be equal to 0, right? Okay,
Mhm.
take a look here. We have two forces, F1 and F2, and take a look at their directions. So we can say F1 minus F2 equals 0, right?
Yeah.
Okay, so what can we get from here? We finally get F1 equals F2. Now what you said, since it's electrostatic, what comes next here? We use
The
we
equation, right?
we use the equation here. Okay, so I'll just write it and then I'll let you calculate, yeah? So this is gonna be K Q Q1 over R squared. D squared, right?
Mhm.
Okay, how far apart are the two? They're 3 centimeters, right? Okay, so this would be 0.03 meters minus D. So it's still gonna be... Okay, I'm gonna write something here. If there's something you don't understand on this last equation here, you let me know.
Okay.
Okay, there.
Um, Wait. Could we do this thing where it was like, wait, I'll tell you the equation. The
Uh-huh.
equations, sorry.
Go ahead.
Uh, F, no, E equals F over Q. So it's equals F over Q2.
Electric fields. You could. You could do that.
And then equal it out and then cancel out Q1
Yeah.
or Q2.
Actually, it's gonna be... You can use that, but using that would basically mean you... how to say that? Okay, if you use the electric field equation, then basically you're going back to this. Okay, because the electric field equation is based on the force equation.
Mm-hmm.
Okay, now okay, so I'll just show you what I mean. Yeah, so okay, so what's the formula for the electric field strength?
E equals F over Q.
Strength. Okay, E over Q. F, yeah, F over Q, right? So electric field. So E equals F over Q. Correct. Now there is another form based on that. This is gonna be K Q1 over R squared, right?
Oh,
Right. So basically, if you move this to the other
yeah,
side,
yeah, yeah.
it still gives you the force equation, right? The reason for that is because the electric field is... this is the definition of the electric field. Okay, so since that's a definition, it will have to come back to Coulomb's law later on. Okay,
Mm-hmm.
so having
So
said
we
that,
can't use this equation,
you
or?
can you can because if you think about it, let me just put this here. You can think about it. Then here, the electric field's going this way. E1's going that way. The electric field here is going this way from E2, right?
Mm-hmm.
And they're in opposite directions, and electric fields are just like forces, they're vector quantities. Since they're vector quantities, directions matter. So what will happen there at the position of Q? Those two electric fields are of equal strength, and no one wins. In a manner of speaking, none of them win. So the charge stays where it is. Okay.
I don't get that.
All right. So basically, what if we do this? so the idea here is that these two electric fields are equal right here, and since they're in opposite directions, the overall effect is zero, right? I can think of it like this. The total electric field would be equal to E1 minus E2, right?
Mm-hmm.
Right? And you know that because of this, you can say that resultant force equals zero, and that's what we're using here. Or you can also say that the resultant electric field is equal to zero. Okay. Now, the reason why you can go here is all you have to do is divide this by Q. Okay. So having said that, either way, it should work. Now, if you do it like this, we know that that's going to be 0 equals E1 minus E2. And therefore, relatively, E1 should be equal to E2, negative. Okay. All right. So if you put that in
Yeah.
here and then you put this back here, or rather not that, but this, if you put this in here, you're going to get basically the same thing. This is going to be K Q1 over R over D squared. That's going to be equal to K Q2 over 0.03 minus D, the whole thing squared. Okay. Now,
Why do we
either
subtract B?
because here's the thing. Remember that the force depends on the distance. So this Q is a distance D from here. But this Q, we know that Q1 to Q2 is 3 centimeters. That's 3 centimeters right there. Okay? Because it's from the same problem as this.
Mm-hmm.
Right? So if this is 3 centimeters, then this is D, then this must be 3 centimeters minus D. And the distance from this charge, Q, to Q2 is this. Okay, so that's why you have to
Mm-hmm.
subtract D from 0.03. You can't use D immediately here. Because remember, the distances should be between the two charges. Okay, so one last thing here. You will notice that the K cancels out with
Yeah.
K here. This K also cancels out with this K here, right? Okay, let me rewrite something. I wrote Q
Mm-hmm.
squared instead of Q2. There. Okay, what else cancels out on the other side? This Q cancels out with this Q. They're the same charge, right?
Yeah.
So in both cases, it doesn't really matter. In both cases, you end up with the same equation. Q1 over D1 at D squared is equal to Q2 over 0.03 minus D squared. Okay, and from here, just solve for D because we do have values for Q. For the Q1 and Q2, we have values.
Mm-hmm.
Okay, so if we finally do this, we get what was Q1? Q1 was 2 microcoulombs, right? Over
Yeah.
D squared. This is going to be 8 microcoulombs over 0.03 meters minus D squared, right? So you can also say that those units cancel out. And then this cancels out. This becomes 1. This becomes 4. Okay. Now, there is a shortcut. There is a shortcut. I don't have to solve for D with algebra. Okay. The shortcut here is that this. Okay, if we go back here, I'm going to say that this is equal to y. Okay. So I
Mm-hmm.
can rewrite this as 4 over y squared, right? So what do we get here now? Y squared over d squared is equal to uh 4 over 1. Okay, but we know that x plus y equals 3 cm. Okay, so I'm what I can do now is I take the square root first, right? So I'm gonna get what
Mm-hmm.
now? Y over d equals 2 over 1.
Two.
So from here we know that y equals 2d. So
Mm-hmm.
we now put this here. Y is 2d, and this should be d, right? So what do we get here now? Um, if so, d plus 2d equals 3. D plus 2d equals 3 cm. So from here, d is 1 cm. So you had two choices. Calculate this using pretty heavy algebra, or just use a different letter and make it easier on you. Which one was easier? In this case, it was using a different letter, right? Okay, but there will be instances where in solving this would be easier. But I'm gonna say that 80% of the cases, using two different letters first and then doing this is gonna be easier.
I just use numeric solver.
Or if you have one, why not, right?
Wait, does this is this the same thing?
Yeah.
Okay.
Hold on, let me see.
Oh,
Yeah, it's the same thing.
okay.
All right. If you have that in your calculator, why not, right? Okay.
Mm-hmm.
All right. So Coulomb's law, uh, pretty straightforward.
Wait,
It
quick question.
Go
What
ahead.
calculator does your school use?
Same one as you do.
Yeah.
But in all
Yeah.
honesty, I don't know how to use that thing to the fullest extent yet.
Do you use the scientific calculator? Like,
I use a normal scientific calculator
oh, okay.
because that calculator, the graphic calculator, is actually much better for math. But we don't really use too much of the math techniques in physics yet. But yeah,
Yeah.
useful.
Right.
There are cases there where it's gonna be useful. Oh, one more thing, since you mentioned that, later on when we're studying electric circuits, specifically Coulomb's law, and no, not Coulomb's law, Kirchhoff's rules, the matrix function of your GDC is gonna be very helpful. Okay, so later on, learn how to use the GDC's matrix functions. Okay, I'll teach you how to do it later. Don't worry if you don't know yet. All right. Oh, let's take a look. It's already 7. We have an hour. You mind if we take like a 3-minute break?
Sure, I need water.
Yeah, all right. 3 minutes. Okay, be back soon.
Okay.
Okay. 3 4 minutes. Fine. All right. All right, I'm back. Let me know when you're ready. All right.
Hello.
Okay. So, all right, Coulomb's law. So, welcome back. Coulomb's law, we're more or less okay, right? You just need to practice probably a few examples later. All right. So, the next two bits, they're related to Coulomb's law. First is electric fields, and then the second one is electric potential. Okay. All right. So first of all, let's go to electric fields. Let's just formally define this first. So this an electric field, okay, is a region where a charge, an electric charge, okay, will experience an electrical force. Okay. So this is the definition of what an electric field is. Okay. Now, of course, with all electric fields come electric field strengths. Stronger fields, so let's just write it here. Stronger electric fields have a bigger, um, will result to a bigger force. Result in larger forces on the same charge. Okay. All right. So that's by definition what an electric field is. And of course, because of the word, this word is deliberate because we now have what we call the electric field strength. Okay. Okay. Now, the electric field strength is basically a measure of how powerful or how strong that electric field is. And by definition, the electric field strength, as you mentioned earlier, this is equal to the force per unit charge. Okay. The smaller the charge, or rather, the bigger the force on the same amount of charge, the bigger the electric field strength. Okay. Now, so that's the thing you've learned. What exactly does it mean? Right? So if you think about it this way, all electrical charges have an electric field around them. Okay? That's the way they exert their forces onto other charges, right? So with this, let's take a look at the electric field around charges, point charges. Electric field around point charges. Okay. The idea here is that if you have a charge, let's say that you have this charge here, and let's say that this is a positive charge, okay? To determine the electric field around it, you must put, so to determine the electric field around the charge, a much smaller positive test charge, and I'm gonna put that here in caps, okay, must be used. Okay. Okay. So the idea here now is, in order for you to determine the electric field around this positive charge here, all you have to do is put like a let's make that really the smallest possible one. Okay. So that's the smallest possible one we can draw. Okay. All you're gonna do is place this small positive charge. This is positive, but I'm not gonna label it as such, and see how it uh moves. Okay. So again, place the test charge near the main charge and see how the test charge moves. Okay. Now we know that in this case, since they're both positively charged, this is gonna be repelled and it's gonna move that way. Right? Okay. Now, similarly, we can move this test charge here and then determine how it moves. We know it's gonna be repelled. It's gonna move this way, right? Similarly, we put this here. Which way is it gonna move? It's gonna move to the right. We put this again here on the left. We know it's gonna move to the left, and so on and so on. So you will see that if the more we put in, the more we put that test charge around the object, the more lines we can kind of draw, right? So we put this here, we draw this here, then we put this here. It's gonna go this way. We can continue on indefinitely by putting it here, 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 but we're gonna stop here with 8. Okay, so in this case, so a positive charge has an electric field, right? That points away from it in all directions. Okay, all right. That's the first thing that we need. Excuse me. That's the first thing we need here. Okay. All right. The second thing that we need to look at is this. Okay. Okay. I'm gonna draw a few more lines so it's a bit more obvious, like this. Uh, like that. Uh-huh. Now, as I draw these, I want to ask you again, going back to Coulomb's law, where would you, where would this test charge experience a bigger force? Closer or farther away from the charge? So again, where will this test charge experience a bigger force? Here, close to the main charge, or here, far away from the main charge? Okay. So in this case, if you think about this, the test charge experiences a larger force when it is closer to the main charge. Okay. That's definitely from Coulomb's law, right? Coulomb's law. Okay. But if you think about it this way, in terms of the electric field, the drawing of the electric field, I want to focus on one thing. Okay, I'm going to use a square here or a rectangle here. I want you to focus here and uh, here. The Okay, so let's call this region A and let's call this region B. Okay, now region A is closer than region B to the charge. Actually, I think I should make it a bit bigger. Okay, and a bit narrower. That's the narrowest it can get. So okay, region A is there. Okay, region B is gonna be here. Okay, so again, region A is closer to the charge than region B, right? Okay, so that is obvious. Now, one thing that may not be too obvious, and that's what I'm gonna try to point out here, is which region has more field lines in it. So which region has more field lines in it? Is it region A or B? Okay, if you look at this carefully, this has 1, 2, 3, 4, 5 lines in, right? 5 lines inside. This only has 1, 2 lines inside, right? Okay. So, in this case, the answer is region A. Has more region A. So what can we put together here? Okay, the stronger electric field has more electric field lines around it. Okay, so the stronger electric field has more field lines inside the same sized region. Okay, region. Okay, now I'm gonna say it in a different manner, but I'm just gonna say it like that first, and I'm gonna say it in a different manner. The stronger electric field has a higher density of field lines. Density of electric field lines. Okay. Now, later on, I want you to keep this idea because this is gonna be how we will define something in magnetic fields. Okay. So um, for magnetic fields, this similar idea will be used about field lines and having densities. Okay. But either way, whether it's gravitational, electric, or what's this? Gravitational, electric, or magnetic fields, doesn't matter what kind of field it is, the stronger field has a higher density of field lines. Okay. So I can cross this out and change this to some other word, and it's still gonna apply. Okay. All right. So that's the second one about field lines. Anything else you'd like to ask before we move on to potential difference? No. Okay. Oh, CJ, just want to make sure you can hear me, right? Okay. I cannot hear you. I think you're on mute.
Wait,
All right. Now I can hear you.
hello?
Yeah, I can hear you now.
Okay.
All right. So you got everything there so far, right?
Yeah.
All right. Great. So field lines, that's a really easy concept to get once you understand how it's done. Okay. All right.
Okay. All right.
Let's go now to potential difference. Now, normally we just call this voltage, right? Normally, right? We're gonna see why it's called potential difference. Okay. Um, I'm gonna touch a little bit of HL material, just a little bit. Okay. Okay. Now
Okay.
the idea here is there's this thing called electric potential. Okay. Just like there's this thing called gravitational potential. Okay. Now, the easiest way for us to do this is in terms of just gravitational potential. Okay. Now, and then later on, we're not gonna go all the way to electric potential. We're just going to link that idea to electricity, and then we'll get to potential difference. But let's start off with this idea of gravitational potential. Okay. Now, imagine if you will. So gravity first, right? Gravity. Okay. Imagine if you will two objects. This object is 1 kilogram in mass, and then this other object is 3 kilograms in mass. Okay. Both of them are equally distant from the Earth's surface. And let's keep it simple. Let's just keep this on the Earth's surface, right? Near the Earth's surface. So this, let's
Mm-hmm.
say that they're both 2 meters off the ground. Okay. So right now, what's a gravitational potential energy here of this 1 kilogram object? Let's just use G equals 10. Okay. Let's assume that G is equal to 10
Okay.
meters per second squared. Okay. So what's a GPE here for the first
Um,
one?
it's and 1/2 mgh. I think it's 10.
Okay, it's not one half. There's no one half in the term, but the rest is correct.
Oh, what?
It's
Oh,
just
so it's
mgh.
20.
It's just this is gonna be 20 joules, right? This is
Yeah.
gonna. How about this other object? The GPE of this other object is
60.
60 joules, right?
Yeah.
60
Also,
joules. Mm-hmm.
is like electrical field strength like similar to gravity in a way, except electrical field strength it like pushes it outwards, but gravity pulls it in.
Now, for that's correct, but think about it this way: electric field strength can also be attractive if the charges are if the charge is negative, right?
Oh, yeah.
Actually,
Okay.
yeah, I kind of skipped that, so we'll get back to that later. But let's get back to this first, yeah.
'Cause-
All right. So the idea here is if you think about this, both objects, right? Both objects have 20 joules of energy for each kilogram they have, right? Okay, so we're gonna introduce this idea now. So let's introduce the idea. Introduce the idea of gravitational potential. Okay, gravitational potential um, is defined, and I'm gonna use a particular symbol, V. This gravitational potential is this V. Okay, and this is equal to the gravitational potential energy per unit mass. Okay, so remember that since everything we have done so far with gravity works with electricity, we can do the same thing, right? Let's do it with this first. Since everything that can be used to describe gravity can also be used to describe electricity, right? We will now use this same idea to define first electrical energy and electrical potential, right? Okay, so that. So this means that there's this thing called electric potential. So VE will be equal to, for now, we will not calculate how we get it, but we will just say electrical potential energy, electrical PE divided by charge. Okay. Okay.
Mm-hmm.
So far, great, right? So we're gonna use that same idea now. So if you have this, let's say that you just have this yeah, let's just say you have this charge, okay, and then somehow when this charge it moves, okay, uh, let's not go to it moves first. So let's just say that at this position, the energy here, the electrical potential energy, let's just give it a value. The HL, by the way, the HL section will describe how to actually get this value. But for now, we're just gonna
Mm-hmm.
assign it values. Okay. So
Mm-hmm.
let's say that the electrical potential energy is 10 joules, and this is 2 coulombs, right? So
Mm-hmm.
from here, we can say that the electric potential is equal to 10 joules over 2 coulombs, right? And that's gonna give us 5 joules per coulomb, right? Now, this joules per coulomb unit has been given its own special symbol. That's 5 volts. So 1 volt is equal to 1 joule per coulomb. Okay. All right. So that's the electric potential. Then let's say at this point, the electric potential energy is now, uh, let's keep it easy first, 0 joules, right? So in this particular case, the electrical potential is equal to 0 joules. I guess that should be obvious on how we got 0, right? Now, if you think
Mm-hmm.
about this now, and this is where voltage, the idea of potential difference comes in now. Okay. Now, in this case, the charge loses energy, right? Somehow.
Yeah.
Okay.
Is it because it's out of the electrical field? So
Not
it's slowly
necessarily.
losing.
Not
Okay.
necessarily. In fact, the electric field is needed for this to lose energy. Okay.
Oh,
All
okay.
right. But anyway, the key point here is that the energy, the charge somehow loses energy, and therefore its energy, its energy, the amount of energy in it in the charge has changed, right? Has changed. Okay. So this change in the amount of energy, we can call that delta E, right? The potential difference is defined, which is also the same as voltage, right? I'm just gonna say voltage like that in quotes for now, okay? The voltage or the potential difference is therefore equal to this change in the energy divided by the charge. Okay? So in our case, the voltage or the potential difference is equal to 5 volts minus 0 volts, and that's going to give us 5 volts. Sorry, this should be volts. Yeah, I forgot that. 5 volts, okay, in electrical potentials. Okay. Now, in most cases, the second electric potential here is usually 0 volts anyway. So that's fine. Yeah. But keep that idea in mind because if I recall right, you are taking HL, right?
No, SL.
Oh, in SL. So in this case, yeah, just think of it like this. Since you're taking SL, just think of it like this. The potential difference is literally the difference in potentials, and the potential is from this idea. Okay.
Mm-hmm.
All right. So in terms of the SL, what do you have to do? In terms of SL, all you have to do is basically say that electric potential difference, uh, potential difference. Okay, I'll just say that here for SL, the electric potential difference. This is equal to the amount of energy lost by a charge divided by the value of the charge. Amount of energy lost by a charge, okay, and then divide this by the magnitude of the charge. Magnitude of charge. Okay.
Was this an equation on
Yes,
the
this is
formula
an.
sheet?
Is this in the formula sheet? I can't quite recall. I better double check. All right, but if it
Is
is,
it V equals W over Q?
yes, it is. Okay. Now, why is it W? Because here, amount of loss,
Word.
yeah, amount of energy lost is basically work done, right?
Mm-hmm.
So that's equal to that work done over magnitude of charge. So in formula, it is, so in this case, V equals work done over charge. That's what that is. Okay. So, all right. I hope that clarifies things and why we call it potential difference. I just figured out why it's called potential difference when I was actually in university. Because I found out that there's this thing called
Mm.
potential. Okay.
Yeah.
All right. Now, so basically we've gone through the 4 equations in the formula booklet. Well, the 5 equations in the formula booklet. There's still a sixth one, right? Okay.
Yeah.
All right. So let's just go through that last one before we go through some exercises, okay? So that equation, I'll just copy that equation from the booklet. Okay. So we have this equation from the booklet. What does this mean, right? This is called, this, not called, this is related to the idea of drift velocity.
Mm.
Okay. Now, what is drift velocity exactly? By definition first, okay? So definition here, definition. Um, this is the velocity, the average velocity of charges in a conductor, that is carrying a current. Now, what do you need to learn here aside from the definition in the formula? Because the formula later on, you just apply it, right? Okay. The thing you need to learn here is what exactly it means as usual. And what we'll do, okay,
Mm-hmm.
hold on. Drift velocity, just gonna get a particular image first, okay? Let's keep it easy to see. This one. Okay, this one's from Wikipedia. This image is straight from Wikipedia, so should be open source. Okay, so let's take a look first. You know that the electrons are negatively charged, right? So keynote, one note, notes. Okay, electrons are negatively charged. And then what we call the conventional current is composed of equivalent positive charges. Okay, so what does this mean? First of all, in a circuit, electrons are the ones that move around, not the positive charges, right? So an accurate description would be all of these electrons, let's say, are moving to the right, right? Now, this is equivalent of
Mm-hmm.
having all these electrons replaced by positive charges and moving to the left. And that's what this current I is about. Okay. All right. Now, having
Mm-hmm.
said that, either way, whether we're dealing with the electrons or those positive equivalents, they have the same charge, right? So to make this easier, let's just look at the electrons. Okay, let's look at the electrons. Um, do, do you recall the charge of an electron?
Mm-hmm.
Okay, the charge of an electron, let's put that here. Charge of the electron. That's the elementary charge. That's going to be 1.6 times 10 to the minus 19 C columns, right? So, um, okay, let's make it more obvious. Now, let's say that these there are, okay, in this wire, I'm gonna give you something. Let's say the wire has let me see, let me think of a number here. Um, okay, okay, let's say that the wire has 8.5 times 10 raised to, let's say, 28 electrons per square meter, per cubic meter. Okay, so this number is okay, so there are 8.5 times 10 to the 28 electrons per meter, and let's say that each of these electrons, okay, I'm gonna look for a number first. Velocity. Okay, let's say that these electrons are drifting at 7, let's make it easier, 5 millimeters per second. Okay, so this 5 millimeters per second is like the drift velocity. So basically, each of those electrons are moving on average at 5 millimeters per second.
Mm-hmm.
Okay. Um, density. Okay. So the question now is, what's the current? So,
Wait, what's N?
okay. what's the current, right? Now, N here is the number of the charge carriers. Okay.
Okay.
Okay. Now, you can actually solve for the current by using that formula, right? So the idea here is N. Uh, Let me double check that. Drift equation. Okay. Uh, N is the density of electrons,
Mm-hmm.
or
When you say current, is that amps?
yeah, in amps. Yeah, this is
Okay.
already in amps. Okay, or free charges. Okay, so it's not all the electrons, but the free electrons or whatever charges you're looking at. So, for example, if the question is it involves ions, and it would be density of ions. Okay, A would be the cross-sectional area of the right there, cross-sectional area of the um conductor. Okay, sectional
Wait.
area.
So is it L?
No, that's A. So A in this case is right here.
Oh, oh.
Okay, so
Yeah.
it's this
Okay.
region here. Okay, V is the drift
Mm-hmm.
velocity. Okay, V is the drift velocity, and Q would be the charge of, well, the magnitude of the charge. In this case, charge of the electron, right?
Mm-hmm.
Magnitude of charge. Okay, so all you have to do now, okay, so before we calculate it, let's see if it makes sense. Well, the amount of current is basically how fast the currents flow, the charges flow. And
Mm-hmm.
the charges, well, the amount of charge that flows depends on two things: the magnitude of the charge and how many of those charges are moving, right? Of course, the faster they are moving, the more charge there is also that flows through. And the bigger that cross-sectional area, the more charges can also flow through. So all of these, increasing all of these, it would increase the current. Okay.
Yeah.
All right. Okay. So what's the current? All we have to do now is put our values in. So the current will be equal to density of the electrons. I already gave you this. This is the density of the electrons, N. Okay. So this is 8.5 times 10 to the 28. Okay, we will multiply that by the cross-sectional area. We didn't give that value just yet, right? So let's say that this cross-sectional area is, let's keep it easy, 1 square meter. Okay,
Mm-hmm.
so in this case, 1 square meter, I'm just going to put 1 for the area. The V, it's given at 5 millimeters per second, so that's going to be 0.005 meters per second. And then Q is this. So 1.6 times 10 to the minus 19. Okay, so we put that in, we calculate, let's see what that value is. Now that's 8.5 exponent 28 times 0.005 times 1.6 exponent negative 19 gives us, that is a big current. Don't worry.
Yeah.
Yeah, what did you get?
I got 66800 something something. Lots
Okay,
of zeros.
6, 7. That's 10 to the 7, right? Amps. Now, just
Yeah.
so we're clear, this is a reasonable answer. This is a reasonable answer because of that huge area we have. 1 square meter is absolutely huge in terms of conductor areas. Okay, normally we have like square centimeters or square millimeters, so that would make it a lot smaller later on. Okay,
Mm-hmm.
all right, so those are all the other three topics that would encompass this particular part. So electric fields done, potential difference done. So again, I just want to note this, that this slide, this is explanation of why it's called potential difference, right?
Mm-hmm.
Okay.
Wait, A is the cross-sectional area of the conductor?
Yeah, the conductor. Okay. Of conductor. Okay. Now, the cross-sectional area, this is perpendicular to current, okay?
Mm-hmm.
Perpendicular to current.
And V is just drift velocity.
Yeah, of the conductor. Okay. Uh, yes. V is the drift velocity. Q is the magnitude of the charge. Okay. Before I forget, this is current, electric current. Okay. Now, of course, okay, I think we're done with this particular bit. So the first part of electricity. There are four main parts, like I said, right? So this is the first
Mm-hmm.
part. It's done. Okay. So let's do some problems. Let me just check problems here, what we could use. Excuse me. Okay, let's do this first. This is the for potential difference. Okay. All right. Since you have your formulas,
Mm-hmm.
calculate this. The work done in moving a charge of 2 microcoulombs between 2 points is that much. Determine the potential difference between the 2 points.
Wait, we use the previous equation, right?
Yes. So which equation do we use? Do we use drift velocity,
Like
potential difference,
the
or
electrical field strength one.
electrical field strength? Actually, use the potential difference here because there.
Oh.
Okay.
Oh.
All right. So let me just copy the data booklet stuff here. Well, I can add a follow-up question here, but we need to go back all the way back to one definition from topic 2.
Mm-hmm.
Yeah. But do this first.
Yeah,
Determine
wait.
the
Could V wait for V, do I just do J divided by the C?
yes. It's that
That's it,
simple.
right?
Yep, it's that simple.
And I was wondering why it was like this.
Mm-hmm.
I got 0.0075.
Okay, let me double check. 1.5 exponent negative. Sorry. Try that again. 1.5
Oh no,
exponent
I got it wrong.
4 negative divide by
I got
2.
7.5 times 10 to the negative 11.
No, I'll tell you this much. Potential differences at this level should be biggish. It shouldn't be too small. It-
But it's 10 to the negative 4, and is that 2 times 10 to the negative 6?
yes, but remember you should be dividing.
I am dividing.
Okay, what you get? I got 75. Just 75.
I got 7.5 times 10 to the negative 11.
Okay. Remember, this is 1.5 times 10 to the minus 4 joules, right? Divide
Yes?
by, V would be this, right? Divide by 2.0 times 10 to the minus 6.
Yeah.
That's going to give us 0.75 times 10 squared. Why? Because this
Really?
negative 6, you're going to have to do 4 negative 4 minus negative 6, right? That's going to give us 2.
The calculator gave me -11.
Maybe just double check. I think you may have not. You may have forgotten the negative for 6,
Um,
which gives us 75.
I put in two negatives.
Okay, 1.5 times 10 to the minus 4 divided by 2, 10 to the minus 6. All right.
I
Anyway, just double check that.
wait. I did that though.
That's weird.
Should I be in radians or like does that not matter?
Doesn't matter in this case.
Wait, are you sure I did it
Yeah,
like
I'm pretty sure you may have gotten a mistake somewhere in there.
like it? Can you see my calculator?
Let me see. Hold on, let me get there. Okay. Oh, okay. All right. Try putting the denominator in brackets.
Okay. Oh, it's different if I put in a fraction.
Yeah. Yeah.
Yeah.
Fraction.
Oh, okay. So,
All honesty, do it as a fraction. Like whenever you're doing a division, better do a fraction. It's gonna give you a better
okay.
answer. Okay. All right.
Yeah.
There we
Then
go.
I got 75.
Yeah.
Yes.
All right. Follow up question. This one's a bit of a challenge. Yeah. You know the
Mm-hmm.
potential difference. Find the electric field between the. Shall we find the electric field? Find the distance between the points. No, never mind. Let's not do the follow up question. Because I have to give you a value. So this is good. Yeah. All right.
Mm-hmm.
Let's do another problem real quick. Not that. Okay, here. This time it's about drift velocity. Okay, let me.
Mm. Do we use the latest equation?
Yes. What's the latest equation here?
The I equals
Yes.
NAVQ.
Yes. You use the drift velocity formula. There.
Drift velocity formula.
Mm-hmm.
Okay.
What are you looking for? You're looking for the drift velocity or the drift speed. Okay.
Mm-hmm. Is A 2 millimeters?
No, that's the radius. So you have to find the area first.
Okay. Uh, how would you do that?
Do you recall the formula for the area of a circle?
No, 2 pi r or something
Okay,
squared.
area of a circle is equal to no 2, just pi r squared.
Oh, okay.
Okay.
What's the Q?
Q is the charge. Now, I'll give you a clue. It says electrons. That should be an automatic value.
Oh, um, is it not the elementary charge
It
thing?
is. It is. So that should be E, right? So I'll just put the value in 1.6.
Is it negative 1.6?
It is, but in this case, it's negative only because it's an electron, right?
Yes.
Okay, but it's okay to use the positive value here because we're looking for a speed anyway. So either way, you'll get the same number because we're looking for speed, not so
The
the
speed I
direction
got
doesn't
was
matter.
negative.
Think about it this way: the negative just tells you the direction, right?
Oh, yeah.
Okay. So what drift velocity did you get?
0.1.
0.1. I got a different answer. Let's see who's correct. I don't know if I'm correct here. Okay.
You. Yeah.
Uh okay. You got 0.1 and I got how much? Let me write that down. 5 times 10 to the minus 5 meters per second. This is
Mm,
also meters per second, right?
yeah.
Okay. Now let's take a look at the equation. So you know that the drift velocity the current rather will be equal to NA VQ, right? We're looking for V.
Mm,
So we're gonna do
yeah.
V will be equal to I all over NAQ, right? What's our current? 1 amp. So just 1, right? Our N is given 10 to the 28. Our A would be pi times uh 2 millimeters. We have to change that to meters. So 0.002 squared, right? Then charge of the electron, that's going to be 1.6 times 10 to the minus 19, right? So the negative actually just doesn't matter because we're still getting the same number, positive or negative. It's got the same magnitude, right? So the idea here now, if we put that in the calculator, what I'm gonna do is I'm gonna do the um 0.002 squared times pi, and then times 10 raised to 28, and then multiply that by 1.6 exponent negative 19. Okay, then I'm gonna get, well, basically that's the reciprocal. This is basically the reciprocal of the denominator because it's just 1, right?
Wait, should it be one more zero? Like 0.0002 or is it 0.002?
This is millimeters, 2 millimeters. This is correct. This is 1, 2, 3, right? Okay.
Okay.
All right. So I'm gonna do that. Yeah, I got the same number, which is 4.97,
Is that to the power of negative 2?
negative 5. This
No, I mean
one?
like,
Oh, right. This should
yeah.
be negative 2. Yes.
Okay.
No, sorry, that's not negative
Wait.
2. That's squared. I'm squaring that because of the formula here.
Okay.
Okay. Now, the reason why I didn't have the negative 2 is because I already expressed this in the decimal form.
Oh, okay.
Okay. So that's positive 2 over there. And since it says estimate, we can just say that's 5 times 10 to the minus 5 meters per second.
You said you got 5 times 10 to the power of negative 5?
Yep.
Okay. Then I got the same
All right, great.
thing with
Okay.
this.
All right, great. Which one haven't been done yet? I guess drift velocity is done, potential difference is done. Electric fields, but you kind of used it earlier already, so I think you get that idea as well. Let's see. Okay. Okay. How about this? Last one for today, and then we can call it a night. Okay.
Mhm.
Last one. Where's the drift velocity higher, and why?
Drift maybe A because it's more concentrated and there's less area for it to go.
Mm-hmm.
But would there be more resistance in A?
Yes, that's true. There would be more resistance in A, but it doesn't matter at this point whether it's got more resistance.
Okay.
Okay, because I'll give you a clue. The currents are equal. The current here and the current here, they're equal.
Um,
That's a clue.
mm, does that mean the speed is equal?
No, not
Oh.
quite. All right, I'll
Wait, I
give.
think B means the speed decreases.
It's slower in A.
Wait, why?
Okay, the correct answer is it's slower in B.
So in B, right?
Yeah, it's slower in B. Okay, slower.
Because the cross-sectional area is bigger.
Okay, so that's not the only reason, but yes, that's the main reason. Cross sectional area is bigger. Okay, cross sectional area is bigger, right?
So that means V has to be smaller,
Mm-hmm.
right?
Okay, so the everything else equal, right? This is the
Yeah.
thing that we kind of missed. Everything else being equal,
Hmm.
equal. This means that V must be smaller. Okay. Now I'll just do that in terms of an equation. Here, the two currents are the same, right? Now I'm just gonna say that this is a cross-sectional area, area 1. This is a cross-sectional area, area 2, right? Where area 2 is bigger, right? So what are we gonna do? That's gonna be N A1 V1 E, right? That's equal to N A2 V2 E. Now the E is obvious why it's the same, but that definitely cancels out, right? But why are the N's the same? The densities are the same because they're the same conductor. They're the same material. Okay? Same material. So so same um electron density. Okay? Now the term used by the book, by the way, is number density, but it's the same idea. Yeah? So these
Hmm.
N's are equal, they also cancel out. So we're left with A1 V1 equals A2 V2. Increasing A, so since A2 is larger, this must mean that V2 is smaller. So it slows down in B. All right? All right.
Hmm.
Okay, so I hope everything's clear. So the rest of the problems in the book, if you can have time to go through them, just do that either on your own or in your class. Okay?
Okay.
All right. Any other questions before we end?
Um, so no, that's good.
Okay, that's good. All right. So we'll end it here. Our next meeting on Sunday, we will go through the next bit, which is electric circuits. Okay.
Okay.
All right. So we'll end it here today. I'll see you next time,
Wait,
CJ.
actually, quick question.
Go ahead.
How would angles affect the electric field, like triangles?
Okay.
Like,
Can you
yeah.
can you elaborate that further?
Like, here's a drawing.
Okay,
Uh,
let me stop sharing my screen first so you can see it. Uh, can you move that over to your right,
oh,
please?
oh,
And a bit lower. Bit lower.
oh.
Determine the electric. Ah, okay. Now, the idea here is that electric fields are vector quantities. They're vector fields. In
Mm-hmm.
other words, you would do this exactly like how you would do a vector. Okay, so
Okay.
let me go to a blank one, and I'm gonna do a similar problem there. Yeah.
Okay.
All right. So for example, what if um I'm just gonna draw it. Okay. What if you have an electric field? This is the first electric field, and let's say that's uh 4 newtons per coulomb, right? Okay.
Mm-hmm.
And let's say that there's a second electric field crossing it like this, right? And say that this is E2, that's 3 newtons per coulomb. Now, I'm deliberately choosing these numbers because we know that this should be an easy solution, right? So what do we
Mm-hmm.
do here? What we do is we're going to draw it exactly like a vector diagram. Solve exactly as a vector diagram. Uh, okay. So what do we mean by that? I'm gonna take one of the vectors. This doesn't have to be to scale anymore because we can solve it, right? So I'm gonna take E1 like that. That's gonna be 4 newtons per coulomb. I'm gonna take E2 and draw it right here, just like exactly again what we would do. This is gonna be your 3. Okay, let's just change that to green. That's your 3 newtons per coulomb. And then your resultant electric field is this. That's the
The
electric field.
distance.
That's it. That's a new electric field. And how do we get this now? The magnitude of this would be 5 newtons per coulomb. Just because it's a 3, 4, 5 triangle, right?
Yeah.
Newtons per coulomb. And then, of
What if you want
course,
to know where the electrical field is at the, what's it called? Where 4 and 3 meet?
right here,
Yeah, at the right angle.
it doesn't matter. It's always going to be the same answer here. Okay? Because here, once you get the vector diagram, the idea now is um, the answer from the vector diagram gives the answer to the actual problem. That's it.
Mm-hmm.
Okay? So again, the main thing about electric fields is that they are vector fields. Electric fields are vector fields, so treat them as vectors.
Yeah, but in my problem where you wrote 5 nano
Now,
coulombs,
newtons per coulomb.
it's newtons per coulombs.
Mhm.
It says for me it's given in centimeters.
Oh, okay. I think that's given in volts per cm,
Wait, never mind, never mind. It
right?
wasn't. It was something else was given in centimeters. It was the
Something
distance
else.
between the three thingy.
Okay. Of course, it still depends later on whether you actually have a varying electric field. But I think at this level, we don't really need a varying electric field, so we're gonna keep it constant.
Mm-hmm.
Okay. All right.
Okay.
All right. Anything else?
No, that's it.
All right. So we'll continue again on Sunday with the next topic. Okay.
Okay.
All right. I'll see you then. Have a good evening.
See you. You too. Thank
Bye
you.
bye now. And we're done with the lesson. So hopefully, this is gonna be okay. See you later.